We've mostly just used the letter R so far to represent correlation. That's a lowercase r, and that is correct notation for any sample, if we're talking about the correlation of a sample. So if we're talking about the correlation of a population, we instead use this more mysterious creature here, which is a Greek letter rho. The way I draw my rho is I exaggerate slightly how italicized it looks. This would be my rho, whereas this would be my P. And if we compare the two, there's a few things that one of them has that the other doesn't. One detail to draw attention to is this little serif up here on the P. You should not have one of those on a rho. There's none of this kind of little mark up here at the top. Another detail that I might call out on the rho is it's a lot easier to make it look different from your P if you put a little bit of a tail swinging to the left down at the bottom, and then you don't do that with your P. Your rho and your P don't have to look perfect for me, but if you yourself can't tell them apart, then it does lead to a lot of confusion. So it's a good idea to just come up with a way of drawing your rho, your Greek letter rho, in such a way that you can always tell it apart from your P. We always use software to find correlation if we want a precise value. We can certainly estimate correlation from looking at a scatter plot and just come up with a number based on whether it's a positive or negative association and about how strong that association looks. But we would never do a hand calculation to find correlation. We'll just use software to find it. And it's very simple. If we go back to the scatter plot we were looking at previously for Hollywood movies with budget as our explanatory variable and world gross as our response variable, we can see that under summary statistics over here on the right, we have the correlation just given to us. So 0.742 is my correlation. Interestingly, this particular data set is considered by Locke to be a population because it's all major Hollywood movies over a given time frame. So we're going to go ahead and call that rho, the correlation between production budget and gross income in the whole population of major Hollywood movies over this time period is 0.742. We identified an outlier earlier, that was the movie Avatar. We're going to go ahead and remove that and see if the correlation changes much. So if we recall, that was up here at 237, 2781.5. Remember to click on this Edit Data button in order to remove a value. And it's hard to find that in the list by just scrolling because this has about 900 ordered pairs in it. So what I recommend doing is a search using Control F. If you hit Control F on your keyboard, you'll notice that this little window down at the bottom comes up, or you may have it up at the top depending on your browser and your operating system. Go ahead and just type in one of the two coordinates that you're looking for. I typed in 2781.5, and when I hit enter, it will highlight it in my list. Makes it much easier to find. Then I can select that whole row and hit the delete key and get rid of that whole ordered pair. We can see that the graph looks pretty substantially different now because the scale doesn't have to accommodate that very large outlier. We can also see the correlation now calculated without it is 0.761. So whether we think that that's a big change or not, it sort of depends on the context. We could answer it either way. Considering that we have nearly 900 ordered pairs, so for n approximately 900, this is a pretty big change just to come from removing one point. But it's not really a big change if we're thinking about the context of would we describe that association any differently, right? For something in the 0.7s, we would still pretty much describe that as a positive association. And that's maybe, let's say, moderately strong. That description would not change based on which of these two numbers I was looking at. So in that sense, it's not a huge change, right? Not a huge change. It can happen for a smaller data set that removing one outlier has a very large change on your correlation. It can even change from positive to negative or to 0 or something like that, depending on the nature of the whole data set. So not a huge change, but a pretty big change considering the size of the data set. Now, I've already promised that we won't be doing any computations with the formula for correlation, but I just want to spend about a minute or two talking about the formula so that you can understand where it comes from. If this here is any ordered pair in my data set, so this is my x sub I comma y sub I, then the contribution that this point makes to the correlation comes from taking that x value and subtracting off the mean of the x's. So all of these formulas are written as if we're talking about a sample, and taking that y value and subtracting off the mean of the y's. So here's my point that isn't one of my data points, but it's just the mean of the x's and the mean of the y's. And then I can break this into two components. The horizontal distance is x sub I minus x bar. The vertical distance is y sub I minus y bar. And the formula here multiplies those two numbers together. There's also a scaling factor. This standard deviation down here in the denominator, it's really just there to make sure that the correlation turns out to equal 1. So this is just a scaling factor. It doesn't really influence anything other than scaling the whole thing down to back to the interval from -1 to 1, which is where the correlation lives. So really the main contribution is just the product of these two values. Now if we look at this example, that x sub I minus x bar is positive, and that y sub I minus y bar is also positive. And so when I multiply these together, I get a positive contribution. Now, if I contrast that with this point down here, which maybe I'll call x sub j, it's just another point, y sub j, I can't make these j's. And look at this line here. This also has a vertical and horizontal component, but this time my vertical component is negative and my horizontal component is positive. So when I multiply these together, this point makes a negative contribution. So the main idea here is that the correlation is calculated from a sum of a bunch of terms that really depend on where they sit relative to that kind of hypothetical point made up of the two means. If you have lots and lots of positive contributions to the correlation, you're going to end up with a positive correlation. If you have lots of positive and lots of negative contributions, you might end up with something that's closer to 0 because they cancel each other out as you add them up, and that makes sense, right? If you're going up from here as often as you're going down from here, then you're not going to have a very strong positive linear association, right? And then similarly, if you have just a lot of points that make negative contributions, you'll end up with a negative correlation. So that's the idea behind the formula. But again, we're not going to really use the formula, nor am I going to hold you responsible for understanding these details of the formula. We just wanted to take a look at it to help to support a little bit deeper understanding of what's going on.